Hello everyone, my name is Denis Antipov, and my talk is dedicated to our joint work with Maxim Buzalov and Benjamin Doyer about the using fast mutation in the crossover-based algorithms. Well, in this talk, I will show you the new algorithm which we have obtained by combining two theoretical results, and then I will prove its effectiveness both theoretically and empirically. Well, let's start with the theoretical discussion of the theoretical results from the point of the regular EA user. Well, they can be divided into three groups. The first one reveals some working principles of the EAs and helps the user to understand how to use the algorithms. The second group gives some design recommendations, like how to set up the mutation rate or the population sizes. And the third group proposes some new algorithms, operators, and so on that the user can use to solve his problems. And usually these three groups don't interact with each other, except the fact that the inspiration for the new algorithms usually comes from the observations of some working principles or from some design recommendations, as it was in case of the fast mutation operator and in the case of the 1 plus lambda comma lambda GA. Well, but in this work we take these two results and combine them into the new one. Well, let me tell about these two previous results first. The 1 plus lambda comma lambda GA is a genetic algorithm which is a little bit unusual because it uses crossover after the mutation. And it works as follows. It keeps only one individual, which is initialized with a random bit string, and then it performs iterations which consist of the mutation phase and crossover phase. In the mutation phase, it chooses some number L from the binomial distribution with parameters n and lambda over n, and then creates lambda individual by flipping exactly L bits in the current individual. And then it chooses the best one as the winner of the mutation phase x dash. The idea behind this phase is to perform a mutation, standard bit mutation with rate lambda over n, but conditional on that all offspring must have the same number of the flipped bits. Okay, then comes the crossover phase, in which the algorithm takes x and x dash and lambda times performs a biased crossover. In this biased crossover, it takes the bits from the mutation winner with the probability 1 over lambda, and it takes them otherwise from the current individual x. Then the best offspring of the crossover phase is chosen, and if it is not was, then the current individual, then it takes its place. Well, this GA was supported by a rigorous theoretical study of its runtime on the 1max problem. It was shown that with static parameter lambda equals to the square root of logarithm n, the expected runtime is n square root of logarithm n, which is better than the runtime of any mutation-based algorithm on 1max problem. However, it was also shown that if we use a fitness-dependent parameter lambda, then we can obtain even a linear runtime in terms of fitness evaluations. However, for sure this is considered as a cheating because we can't use a fitness-dependent parameters in practical problems. And for this reason, it was also shown that using a simple 1/5 rule to control parameter lambda keeps the parameter close to the optimal value, and it also results into the linear runtime on 1max problem. But this simple rule didn't work on a more practical problem, namely max 3 such problem, and it needed some adaptations, namely it needed to cap the maximal value of lambda. And this raises a question: if there is a more universal way to control lambda so that it worked on one max, but it also worked on more practical problems. Well, to answer this question, we decided to consider the fast mutation operator. What's its difference from the standard bit mutation? The standard bit mutation just flips every bit with some fixed probability p. And there is a well-known recommendation to use p1 over n. However, the main issue which we face when we use standard bit mutation is that the number of the bit flips is highly concentrated around the expected value, Pn. Well, for this, to avoid this concentration, the fast mutation operator first chooses some parameter lambda from an integer interval from 1 to u using a power law distribution, and then it performs the standard bit mutation with rate alpha over n. In the book where this fast mutation was first introduced for the discrete optimization, it was recommended to use beta in interval from 1 to 2 and quite high upper bound u. Well, the main feature of this operator is that the parameter alpha is well spread over the integer interval from 1 to u, and also if we use beta greater than 1, we still have a decent probability to choose a constant alpha, including alpha equals to 1. It was shown that if we use the fast mutation operator in 1 plus 1a, then we outperform the standard. Then we are outperformed by the standard bit mutation with the optimal rate only by a small factor on jump problem. However, this happens in a situation where missing the right mutation rate leads to a drastic increase in the runtime. So the main idea is that the fast mutation operator relieved us from choosing the right parameters, and this is what we want to use in the 1 plus lambda comma lambda GE. However, the main question is how to properly integrate these two, this algorithm and this mutation operator. Well, it's this simple. We only add the third line where we, in the beginning of each iteration, we choose parameter lambda from the power law distribution with some parameter beta and some parameter u. We called this slightly modified algorithm the fast 1 plus lambda comma lambda GA to be consistent with the previous results on the fast mutation operator, and everything else is left as it was. Well, and surprisingly, this simple change in the algorithm led us to the linear runtime on 1 max, both in terms of iterations and in fitness evaluations, conditional on that beta is chosen in interval from 2 to 3, and u is the upper bound for lambda is not too small. Well, notice that here the recommendation for beta is different from the previous one for the 1 plus 1 EA on jump k function, where it was proposed to use beta in interval from 1 to 2. Well, to obtain this surprising result, we used quite a simple toolbox, namely the Waltz equation and the estimates of the partial sums of the generalized harmonic series. Well, the Waltz equation is used to analyze the runtime of the algorithm with a variable population size. The main problem for such algorithms is that even if we can estimate the runtime in terms of iterations, it's usually hard to transfer this result into the terms of fitness evaluations, because we don't know what was the population size in each stage of the optimization. However, when we sample the population size from the power load from the same distribution in each iteration, it means that we can use Wahl's equation, which makes this transition as easy as for the algorithms with static populations. Namely, to obtain the expected number of fitness variations, we should take the expected number of iterations and multiply it by the expected cost of one iteration. That's all. However, we still have a problem to estimate the expected cost of one iteration, and we do it using the fact that the cost of one iteration of the 1 plus lambda comma lambda j is 2 lambda, because it makes lambda fitness relations in the mutation phase and lambda more in the crossover phase. And using the estimates of the partial sums of the harmonic series, we can show that the expected cost of one iteration can be super constant if we use super constant u and beta less or equal than 2. However, it becomes constant independently of u if we use beta greater than 2. From this observation, it might seem that large betas are better because they give us a constant population size on average. However, if we use two large betas, namely greater than 3, then the probability to choose super constant lambda becomes too small, and it means that the 1 plus lambda comma lambda GA fallbacks to the simple mutation based algorithm 1 plus 1a and meets all its problems, like the Kaplan collector effect. Okay, so these insights about the population size let us show this full picture of the upper bounds. Well, you can see that the linear number of iterations also can be obtained with smaller values of beta. However, for the smaller values of beta, we have a super constant population size, and it means that the runtime is greater there. Well, and the general rule, which can be seen in this table, is that the smaller betas give us a better runtime in terms of fitness, in terms of iterations, because we are more likely to sample larger lambdas, which make the probability of successful iteration greater. But on the other hand, it also increases the population size, and the trade-off between these two effects is met in the interval between 2 and 3, where we also have a linear number of fitness evaluations. Well, to support this with the lower bound, we want to say that the 1 plus lambda comma lambda j is a comparison based algorithm, and it means that it cannot solve 1 max problem in less than linear number of fitness evaluations. However, we have a simple proof which doesn't require this complexity stuff. The 1 plus lambda comma lambda j flips in each iteration lambda bits at most, and we need to, which is half of the cost of one iteration. And since the initial bit string is in the distance around n over 2 from the optimum, we need to flip n over 2 bits, which means that we need to to perform iterations, the sum of the costs of which is n. Finally, we performed some experiments. In these experiments, we compare the first 1 plus lambda comma lambda j with its competitors, namely with the hill climbers, like 1 plus 1a, with the standard bit mutation and with the random local search, and with the previous versions of the 1 plus lambda comma lambda j, namely with the 1/5 rule, with the capped lambda and with uncapped lambda, and with the 1 plus lambda comma lambda j with static parameters. In the plots shown in the slide, you can see that the y-axis shows the ratio of the number of fitness evaluations to the problem size, and the x-axis has the problem size in a logarithmic scale. In this plot, the horizontal line means that the runtime is linear, and any ascending line means that the runtime is superlinear. Solid lines here correspond to the fast GA. The dashed lines correspond to the hill climbers, and they are both outperformed by the fast GA on the large population sizes. Actually, the 1 plus 1a outperformed in the very beginning. Then the dot dashed lines show the 1 plus lambda comma lambda j with the 1/5 rule, with and without capping. They have clearly a better runtime, but it's not surprising because they both keep lambda close to the optimal fitness dependent value, while we just choose lambda from some interval, and we are likely to choose it wrong. Then the static lambda, which are shown in, with the dot lines, seems to have a similar runtime to the fast GA. However, if you look closely, you can see that they are less convex, and they are actually outperformed on the large problem sizes. Finally, the solid lines, which represent the fast GA, don't look really horizontal, so one can argue that if the runtime of the fast 1 plus lambda comma lambda j is linear. However, they show a tendency to become horizontal, except for the red line, which corresponds to beta equals 2.1. And from this picture we can say that the best choice of parameter beta is 2.5. However, choosing any beta from 2.3 to 2.9 doesn't change the runtime a lot, so they all are acceptable. Well, we also performed the experiments on a more real-world problem on Mach 3 SAT. It is a problem of maximizing the number of satisfied clauses in a Boolean formula in 3 conjecture normal form. And here we used a low density formulas which have n variables and at least 4n logarithm clauses. We chose this problem partially because it has been previously studied in the context of the 1 plus lambda comma lambda j, and it was shown that the 1/5 rule doesn't work here from the box, and it just needed some additional adjustment, which was the capping the value of lambda with 2 logarithm of n plus 1. Well, here we use the same axis, which means that y-axis has the ratio of the number of fitness evaluations to n, and you can see that the fast genetic algorithm shown with the solid lines is outperformed by the random local search and by the 1 plus lambda comma lambda j with the 1/5 rule and the capped lambda. These two algorithms are shown with the dashed black line and the dashed dotted line, blue dashed dot line correspondingly. However, the first 1 plus lambda comma lambda g works quite well here, and it outperforms the 1 plus 1e, and the 1 plus lambda comma lambda g without capping. And the main feature that it works out from the box. And generally the recommendation from this plot which can be given is also to use beta equals to 2.5, but again using any beta from 2.3 to 2.9 doesn't change a lot. Okay, so the take-home message is that the heavy tail parameter choice works also for the genetic algorithms and not only for the mutation-based algorithms, which was shown before. And surprisingly, it not only can relieve us from choosing the parameters, but it also can increase the effectiveness of the algorithms. Well, thank you. That's all.